Good morning students. Today class we are going to discussing about the multiple random variables. In these multiple random variables, the first topic is vector random variables. And what is a vector random variable and how to applying this vector random variable concept on a random variable. Here, why you can consider the multiple random variables, why not consider single random variable? In our science and technology, the most of the experiments and inventions is depending on the two random variable applications. Here the term is a multiple random variables. Here the term is indicating is a multiple means the more than one. The more than one random variable you are using in this unit. Here, among these all random variables, the two random variable concept is very important. The reason is the most of the science and technology applications is implemented based on the two random variable concept. That's why we are going to discussing the entire unit is totally based on two random variables. The first topic in this unit is vector random variables. What is a vector random variable? Already know that is a vector definition. The vector is having the magnitude and direction. But here, can you able to defining what is a vector random variable? For defining this one, we can consider the events in these random variables. Here, we can defining the vector random variable. I have to consider the random variable x is having the event is a small x. Similarly, the random variable y is having the event is small y. These two events is existing on a single sample space, S. Here I am consider two random variables, one is a x and second one is y. The x random variable is having element is small x, the y random variable is having the element is small y. These two are lying on a sample space is S. What the statement is indicates, small x and small y both are lying on a S sample space. Now you can represent the events of random variable x, that one is capital X less than or equal to small x, and the event relating to y is capital Y less than or equal to small y. These events we are representing in sets. The first set is representing random variable x event and second set is representing the random variable y event. Now we can representing these two values on a xy plane. Here I am consider the xy plane. On a horizontal direction I am taking the x, on vertical direction I have to consider y. Here x element is small x, y element is small y. We can representing the small x and small y. It is a random point. This random point you can representing on xy plane. Here I am taking one dot. This point had to give that name is small x comma y. X is relating to random variable x and y is relating to random variable y. Now you can plot the graph between this point and what are the values we are having under random variable x and what are the values we are having for random variable y. For this events is small x and small y, those are having a sample spaces S1, S2. These two are lying in a S. These values I am passing to xy plane. The passing value, the first one is a x and second one is y. This can representing the random point on a xy plane. The random point on xy plane, this point we are calling is a random vector. Say random vector, otherwise you can calling so vector random variable. We can identify any point on a xy plane with respect to the elements of x and y. You can calling the vector random variable. The vector random variable, we can representing this, we can take in the events. Now you can consider the event relating to x is a capital A and the event is relating to y, you can denote it with capital B. Capital B, it is having individual events. Those events we are representing by using the Venn diagrams. By using the Venn diagrams, I have to take the one more diagram. In this diagram, I have to representing same x-axis and y-axis, but in this sample space, I have to representing the events as capital A and capital B. Capital A and capital B. The common part between A and B, we are writing A intersection B. A intersection B. The A intersection B, we are calling a joint function. Is calling a joint function. This joint function can representing on this xy plane. How to representing this joint function on xy plane? Based on the events of random variable x and random variable y, we can able to representing on xy plane. Here you can consider the event A on x-axis, the event B on y-axis. What is the event A? The A event is having the quantity of x is equal to small x and less than small x. Equal to small x and less than small x. That's why we can represent the x quantity on this graph. Here I am taking that the x quantity is a small x. On vertical axis I am taking the y is a small y. Now you can representing the condition of a event A. Event A value is equal to x, equal to x, equal to x means you can take in the straight line at x point, and it is the quantity of x is less than small x. A is less than small x. That means the x quantity is lying in this direction. This is the quantity is lying. Coming to the second one. What is the second one? Event B. The event B is having the quantity of small y. Quantity of small y. The small y is equal to y and less than y. The random variable y is having the quantity is equal to small y or lesser quantity of small y. Already we are denoting the y parameter on a horizontal axis, not a horizontal, it's a vertical axis. We can take in one dotted line at y point. Now we can draw the arrows, the down arrows with respect to the dotted lines of small y. Here I am drawing the vertical lines with respect to the dotted line of small y. Here you can identify which part is having that the combination of x and y. X and y. After small x, there is no common portion between small x and y. After small y in upwards, there is no common part between small x and small y. We can see that the interval of small x and small y, this portion is representing the common part between event A and event B. Event A and event B, the common part we are calling the joint function. We are calling the joint function. We are writing the common part is A intersection B is equal to capital X less than or equal to small x intersection capital Y less than or equal to small y. Small y. Here the intersection part between these two events we are calling the joint function. we're calling the joint function. Can able to applying the probability on this joint function, can calling joint distribution function. Here I am consider the probability for this A intersection B is equal to the probability of capital X less than or equal to small x intersection Y less than or equal to small y. This function we are calling the joint probability distribution function. Can calling the joint distribution function. When out applying the probability for a joint event, we can calling the joint distribution function. Coming to the next part, it is the probability. Can apply the probability on a joint event, we are calling the joint distribution function. The next topic is joint distribution function. We are applying the probability concept on a joint function. We are calling the probability joint distribution function. Otherwise, can simply call the joint distribution function. Here I am writing the joint function is the capital X less than or equal to small x intersection capital Y less than or equal to small y. Can able to applying the probability on this one, can calling capital X less than or equal to small x intersection capital Y less than or equal to small y. This function we are calling the joint distribution function. The notation of this function is capital fx comma y of x comma y. The notation of joint distribution is capital fx comma y of x comma y is equal to the probability of event x and event y intersection. This function we are calling the joint distribution function. Already we are discussing that in the first unit we had to discussing the distribution function. What are the properties we are having under a distribution function? The same properties can be repeating in this unit. Now you can see that in case of discrete random variable, that means for discrete random variable, the distribution function we are representing fx comma y of x comma y is equal to summation. Here you can consider two variables x and y, both are random variables, that's why I can take in the two summations. Here I am taking the m, here also I have to take in that m parameter, both are starting from 0 0, and here ending value I am treating n, here ending value I am treating capital M. We can give the notation is a 0 0, you can representing here n minus 1 and m minus 1. Otherwise you can take in that 1 2, you can representing n. Why? Because we can representing this sequence in a natural numbers. Now you can writing the function of probability of x comma y into u of the step function is relating to random variable x. You can writing x minus xm into the step function is relating to random variable y. You can writing u of y minus ym. This is a distribution function representation under discrete random variable. Suppose you can consider that it is a continuous random variable, you can representing in their density functions. Already you know that for discrete random variable, the graphical representation of a distribution function is step form. For a discrete random variable, the graphical representation is step form. That's why you can using the step functions. For continuous random variable, the distribution function fx comma y is a x comma y is equal to, we can representing in terms of integrations. Here you can consider integral, the double integration of, one is representing the x limits and the second one is representing the y limits. Here you can writing the density function is fx comma y of x comma y into dx dy. This is a representation for continuous random variable distribution function you are representing in their density. For continuous random variable, the graphical representation is continuous. These are the formulas we are having under distribution function. Now you can see that the properties of the joint distribution function. The first property is at minus infinite, the quantities of distribution function is 0. Here I am taking that fx comma y of minus infinite and minus infinite, the value is 0. And fx comma y minus infinite y is equal to 0, comma fx comma y x minus infinite, the quantity is 0. These three properties can be based on their values of single distribution function. Now we can prove this. Already we are saying that the conditions of random variable and the conditions of probability theory. Based on that, here you can consider let capital X and capital Y are two random variables. For these random variables, the x quantity is minus infinite and y quantity is also minus infinite. When I have to applying the probability for x is equal to minus infinite, the value is 0. Similarly, you can apply the probability the y value is equal to minus infinite, the quantity is 0. Based on their conditions, we can representing the distribution function is fx comma y at minus infinite, the value is 0. Why? Because you can already seeing that the probability distribution function at minus infinite, the quantity is 0. And then we are also saying at minus infinite, the probability is also 0. For individual values is zeros, the final value of fx comma y is also be 0. This one is the first property in joint distribution function. In this one, we are also having to take any single value is a minus infinite. Those quantities also be zeros. In joint distribution function. Coming to the next property, the value can be taken at plus infinite, fx comma y plus infinite and plus infinite. The value is 1. Here you can prove this. Just you can take in that what are the conditions you have to consider in the first property. The same you can consider, but you can neglecting the sign of infinite. X value is infinite and y value is infinite. Here x, y both are random variables. You can able to apply the probability on these values. The probability of x is equal to infinite, comma probability of y is equal to infinite. Both are having unity value. We can commonly applying this property on this function. We can finally writing fx comma y plus infinite and plus infinite, the value is 1. This is the second property. Coming to the next property. The third property is fx of fx comma y of x comma y. In this relation, you can make in one value is infinite. You can finding the another value. The third property is fx comma y infinite, x value is infinite, y value is normal. We can obtain the joint distribution. It can be changing to the marginally. Is fx comma y of y. The quantity you can writing is fy of y. How to obtaining this property? You can see here. We are writing the distribution, the joint distribution fx comma y of x comma y. The function we are writing the property of capital X less than or equal to small x intersection capital Y less than or equal to small y. In this case, the x quantity you are consider infinite. The small x is equal to infinite. We can replace in the x quantity in this relation. You can writing the property of capital X less than or equal to infinite intersection the y less than or equal to small y less than or equal to small y. From this, the x quantity is equal to infinite and less than infinite. This can be representing the sample space. You can writing sample space S intersection y less than or equal to small y less than or equal to small y. Already we are seeing that the same concept in last classes. That one is, can consider sample space. In this sample space, as it is having the events of capital X less than or equal to small x and capital Y less than or equal to small y. These two events is existing in this sample space. But here the quantity of x is equivalent to infinite. Infinite means what is the highest value in that region. You have to consider that. Here we consider the probability of capital X less than or equal to infinite. What is the range of x? It is only lying on S range. The infinite means the entire range can be occupied by the random variable x. That's why you can representing this quantity belongs to sample space. The sample space probability you can writing here. That value is 1. But in this case, you can take in that is a complete value is as notation. And one more event is y. This is one event, this is another event. Here, for these two events, you can take in the intersection part. Both A and B, that means X and Y. X and Y both are lying in a single sample space S. Here you can take in the intersection. This is the intersection. But already the S is equivalent to X. That's why one have to take in one higher quantity and one lower quantity. We can take in the operator is intersection. One quantity is a bigger and another quantity is a smaller. What is the common portion between these two? Which one is a smaller quantity is there? It is giving that the common portion between these two values. That's why here the sample space value is a higher quantity and y value is a lesser quantity. That's why the common portion between these two, we are writing the probability of the event y. That one is capital Y less than or equal to small y. This value can representing in their distribution is fi of y. This function you are calling the joint distribution function is a joint distribution function for this value when x is equal to infinite is called the marginal distribution or marginal joint distribution function of a random variable y. You can see that the next property is the fourth one. This one is also similar to this one. Here in third property we can make in that x value is infinite, we can obtain in the y value. This can calling it is a marginally joint function of random variable y. Now you can set the value of y is infinite, we can obtain in the x. You can writing fx comma y, x comma infinite, the function you can writing fx comma y of x. We are setting that the y value is infinite, we are able to obtaining x quantity, can calling it is the marginal joint distribution function for a given joint distribution. Then you can writing is fx of x. You can proving this property, the same concept you can apply here. You can consider the joint function probability. The joint function probability is the probability of capital X less than or equal to small x intersection capital Y less than or equal to small y. Here which quantity can make in infinite? Small y is equal to infinite. Small y is equal to infinite. You can keep this value in this joint distribution function is fx comma y of x comma y. In this relation fx comma y of x comma y is equal to the probability of capital X less than or equal to small x intersection capital Y less than or equal to infinite. Same procedure you can apply here. What are the procedure you can see in third property? The same thing you can apply here. Based on that, you can writing the probability of capital X less than or equal to small x intersection. This entire quantity is replacing with sample space. Here you can observe this model. In this one, you can consider the sample space S. For this S is equivalent to the y value, but x is a smaller quantity, is x less than or equal to small x. This can be lying in S. Now to take in the common portion between S and event of capital random variable x, say event of random variable x, we can take in that which quantities are lesser, it can give the smaller quantity or higher quantity. From these two quantities you can able to writing the common portion is capital X less than or equal to small x. Can writing is the probability of capital X less than or equal to small x. This can be representing the distribution function of x. This can calling a marginally joint distribution function of random variable x. We can denoting with fx of x.